Alright, let me share my screen with you all. I will do as much as I can, and no more. Alright. See what's going on over here real quick. Can we meet Wednesday again like last time to go to the practice exam? Is the 12-pack of due for meeting on Wednesday, or for telling us more, or telling you more than I'm willing? Oh man, I have given up on my diet for the quarantine. Thankfully, I have not put on too much weight since giving up the diet. I will not take the $5 bribe. That would not even get me a 12-pack of dew, depending on where I go anyway. Nope, not 20 either. Okay, let's see. Getting back to where we're going. Let's see here. So, chapter 6, and I think I won't make it full screen just in case I need to go back again some more. So, chapter 6 was a monster of a chapter. Oh, it took me so long to make these videos, and so long for you to watch them. But just to give you an idea of what I'm expecting for the exam, I do expect you to have just general knowledge about how waves work, how to do different calculations with waves, so specifically like relating the wavelength and frequency. You should know how to do that, and if I remember correctly, you will have to do that. It's only been 24 hours since I made the exam, but somehow my mind is... I'm losing my mind, and so I'm 98% sure that you will have to do that on the exam. I think that was one of the blocks of questions where I made multiple questions, and so everyone will do a slightly different variation on converting between wavelength and frequency for different kinds of light. Donuts. Donuts are amazing, although I would have to say dew is more tempting than donuts. I love me a good dewski. Okay, now honestly, how many of you just made a groaning sound at that terrible joke? I know some of you did. I know some of you did. Alright. Yeah, it's a dewski. You never heard of a dewski before? You know, it's pretty bad. It's a pretty bad joke, I guess you can call it. Anyway, moving on. So you should definitely know how to use this equation, because you will have to do that on the exam. Let's see. Here we're talking about diffraction. The only thing I expect you to know for diffraction is that diffraction is something that waves do. It is not something that particles do. So I'm not going to have you drawing diffraction and interference patterns or anything like that, obviously. I'm also not going to give you any questions over why the sky is blue or orange at sunset. That was more just an interesting side note. I do expect you to just generally understand what blackbody radiation is, as well as what the photoelectric effect is. So, just to very, very briefly summarize, blackbody radiation is when things give off light based on their temperature, and the photoelectric effect is when electrons are ejected from the surface of a metal when they are hit by light. So just understanding very generally and broadly what those two topics are, and understanding that these are the two topics that really put the nail in the coffin for classical mechanics. I do also expect you to understand how to calculate the energy of a photon. You will have to do that on the exam as well, so understand how to use these equations, because you will need to use, and again, these are the same equation. It's just this one is in frequency and this one is in wavelength. So know how to use that, because you will need to. Let's see here. So moving on here, talking about light being both a particle and a wave. And actually, we kind of get away from that for a second here. That comes back later. I'm not going to have you using this, by the way. So do not worry about using this equation. This is a very nice equation, a very useful equation in certain situations. We are not going to use it in any of the situations here in the exam. But you did use it on the lab, or at least hopefully, if you've completed the lab. You did that part of the lab because this was in part of the light lab that you did at home. I do expect you to understand that there are only certain energies that electrons can have. This is a big point in quantum mechanics, is that electrons are not allowed to have just any old energy. They are very specific energies that electrons are allowed to have, and they are not allowed to have energies in between those specific values of energy. This is where we get the quantization of energy, the quantization of light as well, is because there are only very specific amounts of energy that electrons are able to have, and those are related to the energy of the orbitals that those electrons are sitting in. Okay, and so this is getting into the de Broglie equation, or de Broglie, if you're American. And so you should be able to use this equation to find the de Broglie wavelength of a particle. And just remember that the mass and the velocity here, they must have the correct units. The mass must be in kilograms, and the velocity must be in meters per second. Up to this point, all the stuff that we've talked about here has been pretty standard in terms of how I would ask questions. So like if I asked you a question over the de Broglie wavelength, it would just be, here's some information, find the wavelength. And so it would just be you typing in the number that you got. And by the way, any answer that you put in, and I think in all of the different questions I did specify this, but just in case I missed one or two questions, you do not have to put the unit in the answer. In the question, I should tell you what unit your answer should be in, and then you will just put the number in. So for example, on a question like this, I would ask you, find the de Broglie wavelength of a neutron at this speed, and give your answer in meters, but don't include the unit in your answer. So you would find the actual numerical value in meters, but you would just leave the meters off. It would just be the number that you put in there. Oh, and also, by the way, and I tried to remember to always put this in there as well, but I might have forgotten a few times. If you have a really, really big or really, really tiny answer, you can use the E scientific notation in the answer box. So if, for example, you find the de Broglie wavelength of something, and it is, I don't know, 1.23 times 10 to the negative 11 meters. So that's the answer you get when you do the math. You can put that into the box where you put your answer as 1.23 capital E negative 11. And Blackboard will recognize that as 1.23 times 10 to the negative 11. So you don't have to worry about counting zeros or putting in superscripts or anything like that. So 1.23 capital E, and it does need to be capital, negative 11 would look, it's read just like this. So Don't worry about, don't try to do point 0.00000000000, however many zeros, 1, 2, 3. Like don't try to do that. If you manage to get the correct number of zeros, it would still count it as correct, but just don't attempt that. Do the scientific notation. It's much easier. All right. Just erase all of this. Okay, so moving on here. This is just, again, talking about wave-particle duality, which I do expect you to know, again, just very broadly what wave-particle duality is talking about. Sometimes things act like particles, sometimes things act like waves. It just depends on the situation. And I also expect you to know that things cannot behave as a wave and a particle at the same time. It's one or the other. Can't be both. Okay. I went through and I told a few stories about this slide here, about the double slit experiment and shooting one electrode at a time, and how in trying to detect electrons behaving like waves. I'm not going to ask you any like specific questions over that, or have you writing an essay or anything like that. That was more just to help you understand the weirdness of quantum mechanics. As far as the Heisenberg uncertainty principle, the only thing that I could ask you over that was just a kind of a general knowledge question, something along the lines of explaining that the Heisenberg uncertainty principle tells us that you can never know a particle's location and its momentum, or where it's going, in a sense. The momentum is where it's going. It's just where it's going is a less scientific way of saying something's momentum. So you can never know where it is and where it's going at the same time. And so that's pretty much all I expect you to know from the Heisenberg uncertainty principle. I definitely do not expect you to be using this equation here. It's not something that you will be working through. And so this is more just talking about the general idea of, since we don't know where the electrons are specifically, we can only talk about where they are in terms of probabilities, and that's really leading up to this stuff here, the quantum numbers, and writing out electron configurations. And you will be writing multiple electron configurations in the exam. Now, the way I ended up doing this is, let me see if I can find a good spot to do this. Here, I'll do it here, I guess. So the way I ended up frozen. What's going on? Yeah, there we go. Okay. Don't know what's going on there. That was a little bit weird. So the way I ended up doing this is I made a bunch of questions where the only thing that was changing from one question to another was the element I was asking you to write the configuration for. And the way I set the question up was I had something like 1s, and then there's a box, 2s, and then there's a box, although the boxes are a lot bigger than this. I didn't realize they would look so big in the questions, but anyway. So 2s, 2p, and a box, 3s, and a box, 3p, and a box, and then 4s, and, whoops, why did I put s4? 4s, and a box, 3d, and a box. And so just, I forget how far I went. I think I went up to like 5s or something like that. So I gave you the correct order of the subshells, and then your job is to put in the number of electrons in each of those subshells. This is the best thing I could come up with to do with this. Unfortunately, that means that I can't have you drawing orbital diagrams, which is a big bummer. It's one of my favorite things to do, is to have students draw orbital diagrams, but there's no way I could figure that out. So if for some, just as an example here, if we were going to do, I don't know, let's say, look at my periodic table here. Say we do calcium. So the question might say, fill in the electron configuration for calcium. And so if you look at the periodic table, calcium has 20 electrons. And so your job would be to say, okay, I need to put those 20 into the configuration here. And so the 1s can hold 2, 2s can hold 2, 2p can hold 6, 3s can hold 2, 3p can hold 6, 4s can hold 2, and that is my 20. And so you will fill in the configuration with the correct number of electrons. So that is how we are going to do electron configurations. It is for sure not ideal, mainly because it's a lot easier for you. So I'm sure that you are just distraught over that. I would prefer that you would have had to write out everything, but that just seemed unreasonable, mainly just because it would, there's no way I could come up with where everyone would have the same way of formatting their answers, which would just mean that I would have to go through and manually check every single one of those, and it would be, with everything else I have going on, I don't have time to manually grade all of those things like that, especially if the formatting is very different. So I settled on this. So this is what we're going to do for electron configurations. No, I don't want to save those. Any questions about electron configurations? You will for sure be doing electron configurations on the exam. I guarantee that. And I might have also put in some questions kind of similar to this one. Trying to remember if I did or not. I know at the very least I was considering it. So you should be able to do something like this, where, you know, if I give you a set of quantum numbers, you should be able to tell me if that set is possible or not, if that combination of numbers is allowed. Alright, so this is just, again, more stuff on electron configurations here, and this is actually where we get into electron configurations in earnest. So lots and lots and lots of stuff here about electron configurations. Like I said, I'm majorly bummed that I can't have you doing orbital diagrams, but I just could not come up with a good way of doing it. You should know how to do electron configurations for ions as well, by the way. That was kind of the one situation where it was a little bit trickier, because you have to remember that if you have a cation, the electrons are going to come out of the where are those? Oh, I guess it's in a later portion here. Somewhere back in here they talk about electron configurations of ions. There it is. So be sure you know how to do electron configurations for ions as well. So again, the electrons, if you have a cation, the electrons that are lost come out of the valence shell first. So not necessarily the highest energy electrons. Let me go back here to where we were. Where were we? Yes, so we're in here, just more electron configuration stuff. Lots more. Again, orbital diagrams. Bummed I can't do those. You should know how to identify valence electrons. So if I give you a question where, like, I just give you a an electron configuration and ask you to determine how many valence electrons there are, you should be able to do that. So again, it's just all of the highest number principal shell. All the electrons in that shell are valence electrons. Let's see here. Irregular electron configurations. Do not worry about those. I'm not going to ask you questions over them. As far as periodic trends, I will for sure ask you questions about these. I think I made a question bank of like, I don't know, 10 questions or something, where I would give you multiple elements and a property, and you would have to tell me which of these elements has the highest value of this property. And so you would have to do that based on the trends. So if I, for example, so like in the slides here, we just did pairs of things. In the exam, I did more than just 2, so I would give you 4 different elements. And there will always be an answer. In the questions that we had here, there was an option where you could not know. So it could be, the trends were opposite to one another. The up-down versus left-right trends were going opposite ways for the pair that I gave you. That's not going to be the case for any of the questions on the exam. There will always be just one answer, not 2 possibilities. So for atomic radius, for example, I could say, you have this element. Oh, it's eraser. Okay. So you could have this element and this element and this element and that element. So you have these 4. Which one is the biggest? Well, it'd be that one, because it is as far to the left as this one and farther down, and so it would be the biggest. And so there will always be an answer. There won't be any situations where you won't know. So there will be questions over trends like these where I'll give you some options and you will have to pick the largest or the highest value. Let's see here. This is more just those trends. I don't think I want to spend too much time talking about each specific trend here. Just knowing all those trends is all you really need to do. So then moving on to the other chapter here, or 2 chapters really. There's kind of 3 big topics in these 2 chapters. There's Lewis structures via CPR, and then polar versus nonpolar stuff. So chapter 7 is really big on Lewis structures. So let me explain how I ended up doing Lewis structures. Again, it's just really difficult to do something where my main way of grading this in an on-campus class would be you drawing something and me looking at it. And that's just completely impossible in this online format. So the way that I ended up doing this is if I give you something like this, C2H4, the way the question will be worded is I will have, and actually C2H4 is not a good example. Let's do this. So BR, it's going to let me draw. There we go. So BR O3 minus. The way the question is worded is something, I forget exactly the way it's phrased, but essentially it says, provide the number of each of the following things attached to the central atom in this molecule in the correct Lewis structure. So your job is to figure out what the correct Lewis structure is. So for this molecule, or ion, actually, if I remember correctly, let's see. I think 2, 3, 4, 5, 6, 7. So I think this is the best Lewis structure here. Although at the time when we were doing this, we didn't. We arrived at a different one. But I believe this is the best Lewis structure. Let me count up the electrons real quick just to be sure. So we have 21 from the oxygens plus 7, it goes 28. Am I counting that right? No, oxygen doesn't have 7. So it's not 21, it's 18. 18 plus 7, this would be 26 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Yeah. So this would be the best Lewis structure. And by the way, this is pretty much as hard as the Lewis structure would get on the exam if I asked you to write the best Lewis structure. And again, the reason that I know this is the best Lewis structure is because if I check the formal charges, which we'll get to in just a second, the bromine is 0, this oxygen is 0, this oxygen is 0, and this oxygen is -1. And that is as low as they can get. So because this is the best structure, the way you would answer the question is down at the bottom of the question there is a spot for single bonds, spot for double bonds, a spot for triple bonds, and a spot for lone pairs. And next to each of these there's a box to put a number in. And so you would write out the hopefully correct best Lewis structure, and you would take a look at it and say, okay, so on the central atom there is 1 single bond, 2 double bonds, 0 triple bonds, and 1 lone pair. And so I can't see the structure that you drew, so if you had something wrong on the oxygens I wouldn't be able to tell that, but at the very least I can tell if you have everything correct on the central atom. And so that is how the Lewis structure questions will be asked, where I will give you a molecule and then ask you to tell me what's attached to that central atom. Not in terms of what atoms or anything like that, but how many single, double, triple, and lone pairs there are. Does that make sense? Other than me forgetting how many valence electrons oxygen has? It is a slightly different way of doing Lewis structures, but it's the best I could come up with at the moment. Okay, I'm going to assume then that sounds fine to everybody. So the next topic there is formal charges and how those relate to Lewis structures. I do expect you to be able to calculate formal charges, either just for the sake of calculating them. So I could give you just here's a molecule, calculate the formal charges, or I expect you to be able to calculate them to find that best structure like I talked about. So you should definitely be able to do that. Let's see, and also I will have you working with molecules that break the octet rule, but I will tell you that. So in the question it will say, like if I gave you this molecule for example, the question would say, describe what is attached to the central atom, xenon. Be aware xenon will break the octet rule. So it'll be something along those lines. I will tell you that it's going to break the octet rule. And so if I don't tell you that, assume that everything is going to follow the octet rule. Unless there's hydrogens, again, because that would only want to duet. But other than hydrogen, everything else should want an octet, unless I specifically tell you otherwise. But there will be questions where stuff will break the octet rule. Alright, so this is more stuff here. I couldn't really figure out a way to do organic molecules because big molecules like that just don't really work the way that I was doing Lewis structures. As far as bond energies and bond length, the main thing that I expect you to know here is just what I talked about in the video. Going from single to double to triple, you get stronger bonds, which means that the bonds get shorter. So those are inversely proportional. So I'm not going to have you working out exact lengths or anything like that, just understanding the relationship between bond strength, the order of the bond, which means, single, double, triple, and the bond length, understanding how those three things are related to each other. Alright, so then via CPR, there was a couple different ways that I asked questions over via CPR. And actually, I'm going to stop sharing my screen for just a second here.